Well, let me mention maybe a less exotic, but well, less common example of a problem. So, for example, I would ask you to tell me what 2 to the power 3.002 is. Can anybody tell me what that number is? Without using a calculator, of course. No? Make a guess. Can you make a guess? 8? So is it really approximately 8? So why do you think it's 8?
2 to the third power is 8.
2 to the third power is 8. But 2 to the second power is 4. And 2 to the fourth power is 16. Why is it 8, not 4, not 16?
It's much closer to 3 than 2 or 4.
Okay. All right. So once you went through this process of making the first guess, let's go through that process slowly and identify what is it exactly that you did. There is something you did to this expression that you never even asked me about, and you never get a permission to do that. Right? So what was it? Well, you changed it. I asked you about this number, right? This is my number, 2 to the power 3.002. And now you are changing that, right? Without even telling me that you are changing that, right? You are changing it secretly. And then you're adjusting it to something you can easily compute without a calculator, and then giving me the answer, whatever you can compute, right? So what does it mean mathematically? Well, that means that you looked at a possibility of raising 2 to some different number other than 3.002. So that means mathematically that you introduced a variable there. Instead of that specific number I gave you, you introduced a variable. And that means you looked at a function. And then if you interpret my question in terms of this function, the question is to find the value of the function at the point 3.002. Right? And what you did is you said take another value which is close to this one, and you picked 3. And you said that that value is a good approximation. All right. It might be a good approximation. Can you tell me more?
You could add on 2 to the 0.002 if you wanted to get an exact, but it's still hard to calculate.
That's hard to calculate. So what can we do? Well, we can do that. Right? So what we can do is we can say that the function, the value of the function at the point 3.002 is approximately the same as the value at 3. And that's what you gave me immediately, plus exactly that term, right? Which is f prime of 3 times what? Yes, what is it that plays the role of x in this example?
3.002.
Yes, that is going to be x0, right? A good point, and that is going to be, oh, no, is that good? No, it's bad. It's a known, right? It's strange point, and this is x0, a good point. So you evaluate derivative at that x0, you multiply by x minus x0, and then calculus suggests, well, this is a better approximation. Well, can you compute it? Well, in order to compute that, you need derivative of that function. Do you still remember what derivative is? Of 2 to the power x? Can someone tell me, please?
1 over ln 2 times 2 to the x.
It's 2 to the x times ln 2, which is very close. So, well then, we can use that. So my number, right, is approximately f of 3, which is 8, plus the derivative evaluated at x equals 3. It is 2 to the power 3 times natural log of 2 times the difference, and that difference is 0.002. And if you notice that, well, this is exactly what makes this number small. Right? And then, so what is it approximately? Well, what is natural log of 2? Well, let me approximate it by 1. Is it kind of close? Well, then, what I have is 8 plus 8 times 0.002, which is 8.016. Does anybody know the exact? Well, let me show you the exact value. So this is my favorite way of finding exact values. Wolfram alpha. It allows you to type in any question in one line. And my question would be what? 2 to the power 3.002. And that's the interpretation, which is correct. And that's the exact value, which happens to be 8.011. What else? 1. So I got 2 more decimal places without any calculator. So this is all done by one step, by computing one derivative. And well, I can go further because well, that approximation is kind of rough. So what can I do about that? Can I find natural log of 2? Well, how can I do it without calculator? How can I estimate it better than just 1? Can you approximate it better? What would be the number you substitute instead of 2, which is close to 2, and you know exactly the value? E, yes. You know natural log of E. The value is 1. All right, so this is a good number. And then I can write natural log of 2 approximately as natural log of E plus what? So what am I doing here? I'm looking at the same thing with a new function. G of x equals natural log of x, right? My question is about the value of g at the point x equals 2, which is bad. But the value x equals e is good, and e is close to 2, so what is the next term? It's derivative of that, right? It's derivative of natural log of x evaluated at x equals e, right? Multiplied by two minus e. Well, you have to be precise about that, because changing the order changes the sign. Okay. So you subtract bad number from, good number from bad number. And then what? What's the derivative of natural log of x? G prime of x is very easy. It's 1 over x, right? So that is natural log of 2 is approximately 1 plus that derivative at x equals e makes 1 over e times 2 minus e. Well, if I multiply through, I get 1 plus 2 over e minus e over e, which makes 1. 1 cancels. And the whole thing is equal to 2 over e. So that's what natural log of 2 approximately is. Well, still kind of, what is it? Well, if you divide 2 by 2.7, what would it be? It will be approximately point what? 0.7. Multiply 7 by 27, get 189. 189 is close to 200, so that's what it is, 0.7. Now, what if I take that and replace 1 with 0.7 in my previous approximation? What if I compute 8 plus 8 times 0.7 times 0.002? How good is that? Well, it is 8 point what? Definitely 0, and then I have to multiply 8 by 7, 56 by 212. Right? So I get 8.0112. And now I have 3 decimal places without any calculator, using only 1-digit approximations all the way. Right? So that's the power of first derivative of calculus. And, well, unfortunately, you cannot go much further using just first derivative. That's pretty much where you stop in this problem. And, well, to go further, you need Taylor series. That's probably what you have already started studying in calculus 2. Have you studied Taylor series? Well, it will be one of the central pieces of our course. So we will quickly refresh that and we will use it all the time.